Hello again. I wanted to revisit the problems that we saw in the very first topic, the tangent problem and the velocity problem, because now we have a new way to look at things. We have a new notation, and we have some techniques that can help us approach the problem in a different way. So I felt that it was important to go back to those problems and look at them again from a new perspective. So if we think about where we started, we were talking about this thing called a secant line, and we found the slope of that secant line, and through a process, through a limiting process, we learned how to find the slope of the tangent line. So let's look at this problem again. What we said was, basically, if we let this point, this x value be a, then we had a point a comma f of a. And then we had another point, and let's just put it here and say that this x value was b, and so then this point up here was the ordered pair b f of b. And we saw that the average rate of change, the slope of the secant line, was an average rate of change and that was given by just finding the slope between those 2 points. So using the traditional slope formula that you learned back in beginning algebra, that was f of b minus f of a over b minus a. And then what we did was, we said, well, now take this point b, and drag it closer and closer and closer to the other point A. And so what we did was we took that B value and got it closer and closer and closer to A. And so what we were doing is using a limiting process. And if things worked out nicely, which they did a lot of the times, we got the slope of a tangent line and that's something that we call an instantaneous rate of change. And we can now express that using this notation. That is the limit with b approaching a of f of b minus f of a over b minus a. And so if we just have the slope of the secant line, if we just an average rate of change, that's just the slope between 2 points. However, if we apply this particular limiting process to it, we get the slope of the tangent line, the instantaneous rate of change. And we can also use the same notation for an average velocity versus an instantaneous velocity. Where instead of having a general function, if we started with a position function, then we get an average velocity or an instantaneous velocity through these same processes. So this is a really important concept because this slope of the tangent line, this instantaneous rate of change, leads to something more. And if we sort of think about this limit right here, notice I cannot directly substitute b. All right, or if I'm letting b approach a, I cannot directly substitute a, really, because then that would give me f of a minus f of a, which is 0 in the numerator, and a minus a in the denominator, 0 in the denominator. It's an indeterminate form. We have to use the techniques that we learned in the previous topic to work through this situation. Let's now introduce an important alternate view of that same problem. Let's again start with our generic function and our point A. And so a f of a. That's the actual point on the curve. But now, instead of marking another point on the x-axis as being where the x value is b, instead, let's introduce a distance from A. Let's call the distance from A, let's call this distance right here h. And so now, my second point on the x-axis would be the original A distance plus this h distance, right, this change. And so now this second point is A plus h. That would be the x value is now A plus h. And so then this new point on the curve has x coordinate A plus h and y coordinate f of A plus h. And so then, using these points, we can come up with an equivalent average rate of change. The average rate of change, which I'll just abbreviate AROC, the average rate of change would simply be the slope between those 2 points. It would be f of A plus h minus f of a, change in y, over the change in x, which would be A plus h minus a. And so then this simplifies as f of A plus h minus f of a. And then in the denominator we have A plus h minus a. Hey, that's simply h. The change in x, right, the change in the x values is simply that distance h between them. Then, if we wanted an instantaneous rate of change, IROC, well then all we would have to do is say, well, take this h value and get it close to 0. If we can get that h value close to 0, that gives us the instantaneous rate of change. And so that's again a limiting process. The instantaneous rate of change can be expressed as the limit with h approaching 0 of f of a plus h minus f of a over h. And again, notice that we cannot directly substitute h equals 0 here. Because if we directly substituted h equals 0, then the numerator would become f of a minus f of a, which is 0. And the denominator is obviously 0. And again, we have an indeterminate form. So we have to manipulate this using the techniques we've learned in the past. So let's see an example of this. And again, for these average rate of change and instantaneous rate of change, I could equivalently say slope of the secant line versus slope of the tangent line. If this was a position function, I could say average velocity versus instantaneous velocity. It's the same concept, same notation. So here's an example. If the function is x squared plus 3x, find the slope of the tangent line when x equals 1. Alright, so using the first approach, when x equals 1, with a equal to 1, then the slope of the tangent line is the limit as b approaches 1, where b is some other value out there, and I'd have f of b minus f of 1 over b minus 1. Now, I cannot directly substitute, because if I substituted b equals 1, I'd have f of 1 minus f of 1, which must be 0 in the numerator, and then 1 minus 1, which is 0 in the denominator, an indeterminate form. All right, so let's use some substitutions here. This is still the limit with b approaching 1. F of b. Well, if f of x is x squared plus 3x, then f of b is b squared plus 3b. F of 1. All right, so simple substitutions. 1 squared is 1. 3 times 1 is 3. 1 plus 3 is 4. All right, so I've made the substitutions. Now, you should be able to use the techniques we've learned in the previous topic to evaluate the limit from this point. Now would be a good time to pause and try that out on your own. All right, so what I would do here is notice that I can write this numerator as more simply just b squared plus 3b minus 4 over b minus 1. And notice that the numerator factors as b minus 1 by b plus 4 over b minus 1. So I can remove the factor of b minus 1. Then this becomes the limit with b approaching 1. And I've removed the common factor of b minus 1. And so then this would be the limit with b approaching 1 of b plus 4. Now there's no issue. It's no longer indeterminate, and I can substitute b equals 1. And so then this would become 1 plus 4, which is 5. So the slope of the tangent line to that curve when x equals 1 is 5. Let's now show the same problem with that second approach. Again, we would have with a equaling 1. So then we would have the limit with h approaching 0, and then I'd have f of 1 plus h minus f of 1 over h. Now again, I cannot use a direct substitution here. All right, so instead, let's try some algebra. Let's manipulate this. So this becomes the limit with h approaching 0. F of 1 plus h means I have to take this function, and everywhere that I see the x, I have to replace it with 1 plus h. So this is going to become 1 plus h squared plus 3 times 1 plus h. All right, so we have that. I'm going to just bracket that just so you can we can clearly mark where it begins and ends. Then f of 1, well, f of 1 is still 4, right? That hasn't changed, over h. So now, again, what I would suggest is you should be able to take this, from this point, you should be able to evaluate the limit from this point. So now would be a good time to pause, try that out on your own. All right, applying a little bit of algebra here. This becomes the limit with h approaching 0. 1 plus h squared, remembering how to square a binomial, that would be 1 plus 2h plus h squared. Then applying the distributive property in the second term, plus 3 plus 3h minus 4 all over h. Let's simplify the numerator, combine like terms. All right, so let's see, I have a 1, I have a plus 3, that's 4, minus 4 is 0. That's nice. Let's see what else I have. I have a 2h and a 3h. Those combine to 5h. And then I have the plus h squared. It doesn't combine with anything. Over h. Again, I can do a little factoring here. notice that the numerator can be written as h times 5 plus h, and the denominator is still h. Notice that I still could not directly substitute 0, because the numerator would become 0 and the denominator 0. It's still indeterminate. However, now that I have the factored form and I can remove the common factor of h, this then becomes the limit, with h approaching 0, of simply 5 plus h, which is then, now I can substitute 5 plus 0, which is 5. And so I got the same result using either technique, which is a good sign, right? I mean, if we got different results, then that would mean that we either the two techniques weren't equivalent, or I did some error in the middle. So this is a new approach to those same problems. And one thing that's really important is this idea, this limiting process is going to lead to a whole new area of mathematics. And we're going to get there in a couple sections. So, sort of a teaser, but we're going to get to something that I think is really interesting in just a couple sections. All right. Thanks for watching. I'll see you then.